Okay, this video is the second part of our discussion of internal effectiveness factors. We're going to consider Thiele moduli and effectiveness factors for different geometries than the spherical case that we've already done. We're also going to consider different rate laws, and we're going to consider the effect of a diffusion limitation on an apparent activation energy. And we may get to some examples as well. All right, well, the problem that we just solved was the Thiele modulus and effectiveness factor for diffusion transport coupled to chemical reactions happening in a sphere. The non-dimensionalized version of the species balance equation is given here. Recall that was our Thiele modulus. This was its definition, k cat r squared over the effective diffusivity. And this was the solution. This was the effectiveness factor. And this was the asymptotic behavior of that effectiveness factor in the limit where the Thiele modulus becomes large, okay? So when you have a severe diffusion limitation. You can also solve the problem in a slab geometry. So you had like a flat layer of catalyst, for example, and it was a porous material with a concentration given at the surface and no flux through the back wall. Then this is the species balance equation that you get. There's the Thiele modulus again. The definition is slightly different, but basically the corresponding thing. You've got k cat now times the relevant length scale defined to be the thickness of the slab. Notice that the slab is defined as having an impermeable wall at the back side. So if you had a slab exposed to the gas on two sides, you would use half of the length and get the same kind of solution here by symmetry. And the solution, because of the geometry difference, now looks a bit different. They're cosine hyperbolics. The effectiveness factor is tangent hyperbolic of the Thiele modulus, all divided by the Thiele modulus. And now, in the limit, as the Thiele modulus becomes large, the asymptotic behavior is 1 over the Thiele modulus. You can solve the problem as well for a cylinder case. The partial differential equation that you get is a bit more complicated. It's going to involve Bessel functions. The geometry gives rise to the same definition of the Thiele modulus as we used for the sphere. And I won't go through and talk about these very much. These are modified Bessel functions. But the main point is that you can, again, get a closed form expression for the effectiveness factor, and the asymptotic behavior now is 2 over the Thiele modulus. So these are pretty easy to remember. If you have one-dimensional transport into a slab, you get 1 over the Thiele modulus. If you have 2 dimensions for transport to the center of the cylinder, then you get 2 over the Thiele modulus. And if you're in 3 dimensions where transport to the center of the sphere happens from all 3 directions, you get 3 over the Thiele modulus. All right, so if we take that eta versus phi relationship, that's the effectiveness factor versus the Thiele modulus, and put them on a log plot, all 3 of the relationships for spheres, cylinders, and slabs show a similar behavior. At very small values of the Thiele modulus, you have a plateau at 1 in the effectiveness factor, and at very large values, these things drop with a slope of -1 on the log scale. The key difference is that they break off from that plateau at eta equals 1 at different places. Remember, the slab behaved like 1 over phi, and the sphere behaved like 3 over phi, with the cylinder in between them at 2 over phi. Okay, let's do an example to see how we use these effectiveness factors in Thiele moduli. You will notice that the first application that I want to illustrate is actually not a catalysis problem, right? So we're going to think about cells within a biofilm, the little dot things in here, and they're dispersed at some concentration C sub C, the concentration of cells. And they're going to consume a nutrient A at a rate that's given by KCA. Now, that's the rate of consumption at each cell, nutrients per time. Then we can multiply that nutrients per time by the concentration of cells that are doing the consumption, and we get molecules of A consumed per volume per time. So that's this term in the balance equation on species A. The nutrient actually arrives at the surface where its concentration is Ca sub S, and it diffuses down through the biofilm to reach the cells deep in the biofilm. This is going to be a diffusion reaction balance problem. At steady state, with no convection, if you develop this balance on species A, you find that it's the same equation that we've been solving before. Now there's a subtle difference here. K cat has become Kc sub C. But that's okay, that doesn't matter. It's still the same type of equation. Remember, they're uniformly dispersed throughout here, so it doesn't depend on where we are in the biofilm. the concentration of these cells. And so this is effectively exactly the same kind of problem that we've been solving. If we non-dimensionalize this equation, sorry, let me declutter this thing. And if we non-dimensionalize this equation the same way that we did before, using that as our dimensionless concentration, and this variable xi as vertical height divided by the thickness of the biofilm is L, then we get a Thiele modulus that pops out. And that's this right here. Okay, so now this is a slab geometry, and it's a first order reaction. So the effectiveness factor is going to be tangent hyperbolic of phi divided by phi. And now the question asks, what is the effective steady state rate at which the biofilm consumes species A in moles of A per biofilm area per time? How fast would species A be consumed if the entire region in the biofilm was at the surface concentration of the biofilm? Then we would multiply K by that surface concentration to get the rate of consumption at each cell. We would multiply by the concentration of cells to get the consumption per volume per time in the biofilm. Then we would multiply by the depth of the biofilm times the area of the biofilm to get the total moles consumed per time. We would then divide by the area again. And so the only thing you see here is this factor of L. So that's the depth of the biofilm. This factor right here, this is the focus of this lecture, is correcting for the fact that the entire biofilm is not at this concentration Ca sub s. It is a declining concentration because of the competition between consumption by reaction and replenishment by diffusion supply from above. So this eta factor builds in that correction for us, and we don't have to resolve the whole partial differential equation to get an expression. We could just write down the rate in terms of this tabulated Thiele modulus and effectiveness factor. Let's walk through another example, and in this case we're going to look at how the presence of a severe diffusion limitation will affect the apparent activation energy that an experimentalist would see from an Arrhenius-like analysis of their data. You might initially think, well, if it's a severe diffusion limitation, then of course the rate is really limited by diffusion, and so I should see almost no activation energy at all. But you could also argue, well, there's nothing being consumed if there's no reaction at all, and so maybe there should still be some reflection of the activation energy there. We're going to just follow the math and see how this comes out. We're going to consider a first-order heterogeneous catalytic reaction. It's going to occur in a spherical pellet, although you will see that that has no bearing on our analysis. We're going to assume that we're in the limit where we have strong internal diffusion limitations. Let's see how the observed rate depends on temperature. In the case where the kcat has an Arrhenius-like temperature dependence, the effective diffusivity also is going to have an Arrhenius-like temperature dependence. Now, we can always switch that to something with a very weak temperature dependence by making the activation energy for diffusion, this E sub d, be very small. Okay, so the observed rate is going to be the rate as though the reaction was happening at the surface concentration multiplied by the effectiveness factor. So this is the rate now averaged over the whole pellet, accounting for the effects of these diffusion limitations. And remember that when we're in the limit of a strong diffusion limitation, then eta is approximately 3 over phi. Okay? So that means that if we write down the rate that we would observe here, we would get kcat times Ca sub s times 3, and I've written out the Thiele modulus right down here, the square root of kcat times r squared divided by d. And now what I'm going to do is just collect all my terms and move everything upstairs with the appropriate power. So I've got a factor of 3, an r in the denominator. I've got a factor of Ca sub s, and I've got a d to the 1/2 and a kcat to the 1/2. So, of course, 3 and Ca sub s and r, these are not functions of temperature. So when we do our Arrhenius analysis, and we take the derivative of the log of the rate that we observe with respect to 1 over temperature, all of those factors are going to fall away. The factors that remain are coming from the kcat and the d to the 1/2, which are functions of temperature. The logarithm of a product is the product of the logs, and when I take the logarithm of something that is raised to a power, the power 1/2 in this case comes down front, and I get that the log of kcat to the 1/2 is 1/2 the log of kcat. Okay, so that's what's happened right here. You see the 1/2 of kcat and the 1/2 of log d derivatives. And these are being differentiated with respect to 1 over t. And by definition, remember, these were defined with Arrhenius type temperature expressions. They were these expressions right there. And so we know by construction that what's going to happen when we go through and take those derivatives with respect to 1 over t is that this term is going to give E sub a over 2, and this term is going to give E sub d over 2. So interestingly, the activation energy that the experiment would appear to see is not the intrinsic activation energy of the chemical reaction step, but a 50-50 mixture of the activation energy of the chemical reaction step with that activation energy associated with the diffusion resistances. And this is often very small. So in many cases, ED will be very close to 0 compared to the size of EA, and that results in the observed activation energy appearing to be half as large as the real one, which is a fascinating result. If you go through and you do this for other geometries, you see that all they do is they change whether this was a 3 or a 1 or a 2. And so this is a very general result.